Hi, Honors Chem. I just wanted to talk a little bit more about phase diagrams today. We are also going to start doing the quantitative work of trying to figure out exactly how much energy is going back and forth between some of these phase changes and temperature changes that we observe as well. So we're going to introduce some of that today. I wanted to go back to the phase diagram that we went over last time of water. And I wanted to point out something that's really different on the phase diagram of water compared to other phase diagrams. And that is this. So if we look at the line between the liquid and the solid phase, and it's the line that's highlighted in red, I'm going to put a yellow highlight next to it so that you can see what I mean. If you look at that line kind of tilts backwards. It has what we call a negative slope. And it means something pretty interesting is when we create a lot of pressure. So, for example, if I let's start right here, and if I put a lot of pressure, same temperature, but if I put a lot of pressure in, eventually I will make that solid go to the liquid phase if I get enough pressure. And we capitalize on that when we ice skate, and we talked about that a lot. This backwards, barely backwards, but this backwards leaning line between the solid and the liquid phase definitely shows that the density of liquid water is greater than the density of solid water. This basically shows that the expansion of water happens when it freezes, which is the opposite of other compounds, because normally when another compound freezes or becomes solid, it actually condenses a little bit more. The solid is actually the smaller phase, but water is different. It expands when it freezes. Okay, so remember the important points. We have our normal melting point. Remember, that is at 1 atmosphere. We have our normal boiling point that is also at 1 atmosphere, or standard pressure, 760 millimeters of mercury, or we could also say 101.325 kilopascals. And we also have the critical temperature, and that critical temperature is the temperature above which we can no longer really tell whether we have a liquid or a solid. It becomes what we call, or not a liquid or a solid, a liquid or a gas. It becomes what we call a superheated fluid, and we can't really liquefy it anymore at all. Okay, so we also have our triple point, and our triple point is where we have all three, solid, liquid, and gas, all three phases in equilibrium at the same time. Okay, hopefully you looked at that triple point video. Okay, let's go and look at the phase diagram for carbon dioxide. Notice the phase diagram for carbon dioxide is a lot different than the phase diagram for water. First of all, notice that this line right here that I'm highlighting in yellow between the solid and liquid phase actually has a positive slope instead of a negative slope. That means that carbon dioxide is more dense as a solid than it is as a liquid. This is a more normal phase diagram for a compound compared to the water phase diagram. Okay, notice that if I started somewhere here in the solid area and kept on putting pressure on it, it would still just remain a solid. It's not going to become a liquid like water is. Okay, so notice also, here's our triple point. Okay, and it doesn't even show us what that critical point is because it only goes to 31 degrees Celsius. Notice though, at 1 atmosphere, normal pressure right here. When we hit that first phase boundary, we are still in the sublimation line between solid and gas. So the melting, I should say not even melting, the subliming phase point for carbon dioxide is negative 78 degrees. So at 1 atmosphere or standard pressure, CO2 doesn't ever hit the liquid area at all. It just sublimes. So in normal pressures that we would actually have carbon dioxide in our normal atmosphere, we as humans would never ever see carbon dioxide in the liquid phase. In order to see it in the liquid phase, we would have to really increase the pressure. So we would have to put it in a pressurized chamber to see it. Okay. Let's see. So we talked about what the significance of that line is. The significance of that solid liquid line for water and CO2 being different, it means that carbon dioxide solid is more dense, dense than carbon dioxide liquid. And the water is the flip side. Water solid is less dense than H2O liquid. That's what the different slopes on those line means, okay? So the carbon dioxide, this is normal. This is how most compounds react. Because water does this, it's highly unusual. Can't spell. All right. It's so strange. Water is really the only thing I know that does this. Okay, so let's look at this next one. We want to use the table below to create our own phase diagram. Okay, so it doesn't have to be perfect, and we're not going to draw anything like super demanding. Okay, and of course it doesn't. There we go. So we're going to use the triple point. Okay, so we are going to do this for ammonia here. So we've got our triple point of 0.060 atmospheres. So notice this is super low. So let's look at the different atmospheric pressures that we have to look at. We have to go from way less than 1 to way more than 1. Okay, so we are going to have to really change the scale here. Okay, let's see. Why is this not letting me write? I don't want to. Can we cancel this? Nope. And because of this, it's not going to let me write. All right, so I don't know why. Yep, it's going to keep on being fuzzy. So let's see if I can get this to design and cancel this layout. There's something about Screencastify and Word that doesn't like to play nicely together. It really doesn't want to think about this.